Hello, professors and respected audience. I'm Amir Elzwawy. I'm giving the presentation today entitled Buffer and Cabin Layer Impact on Exchange Bias and Planar Hall Effect Sensors Profile for Nickel and Gold Iridium Magnesium Films. Outline for this work starts by the introduction, where we gonna overview for the sensors and the Planar Hall effect, and to show the motivation of the work, followed by the experimental procedure for the fabrication steps, and heading to the results where the seed and cabin layer effects on the exchange bias will be revealed, as well as their effect on the output voltage, and finally the conclusions for the work. The sensor's overview lies in four stages. Firstly, starting by the geometry optimization, where different junctions can be optimized or prepared, such as the cross junction, multi-ring, and diamond shape or bridge configuration, followed by the structure optimization for different structures, such as bilayer, trilayer, and spin valves, and the optimization for the parameters where they are important for the sensors, such as the exchange bias and the magnetic resistance value, and finally the integration possibility for these sensors onto devices. In general, sensors need some kind of basic requirements such as high sensitivity, accuracy, and thermal stability, as well as less power consumption and enhanced resolution. The planar Hall effect is a unique type of magnetic sensor, and in brief, it is referred as the Hall configuration added to in-plane applied magnetic field, and they have some kind of advantages such as high signal to noise ratio, low offset, high resolution, high linearity at small fields, as well as reduced thermal drift. In this work, to use the nickel iron chromium seed and cabin layer, we were motivated to use them because it is reported in the literature that the use of nickel iron chromium with nickel iron as a single layer gives increased magnetic resistance value, as well as the introduction of the gold spacer layer versus the copper spacer layer. It has increased sensitivity as well as better thermal stability. Hence, we thought about combining both in one structure. For the fabrication of the sensors, they lie in two stages. First stage is the junction fabrication, and the second one is the electrodes fabrication. For the junction fabrication, we have the combination of photolithography and the sputtering technique, where we have the photoresist material onto the silicon substrate, followed by the soft baking and UV exposure and developing and the deposition of the desired thin film structure using sputtering, and finally we get the batter. For the electrodes, we follow the same process, but using another target with the gold. And finally, we get the sensor as displayed in the photo. The seed layer effect on the exchange bias. When we use nickel iron chromium instead of tantalum as a seed layer, there was an increase in the exchange bias, and it was revealed as a shift of the center of the hysteresis loop from the zero to a specific point, and this might be regarded to multiple origins, like the formation of the magnetic dead layer between tantalum and nickel iron, or the chromium diffusion onto the nickel iron. But the most probable explanation of this increase in the exchange bias was the change in the tensile strain distribution in the nickel iron layer and the corresponding changes in the roughness, where they give rise to the exchange bias value. Completing with this one. When we use the nickel iron chromium as a capping layer instead of tantalum, we get 3 times increase in the exchange bias value. And this can be explained by the fact that depending on the difference in the mass, in the atomic mass for the tantalum and nickel and the iron and chromium, almost the tantalum is 3 times higher in the mass. It differs in the effect on the gold spacer layer in between the nickel iron and iridium manganese, and hence different coupled and decoupled areas can be obtained because of the transfer of the momentum due to the higher mass of the tantalum, and subsequently a difference in the exchange bias value is performed and is obtained. And this was affirmed by the atomic force microscope results. To show the effect of the seed and cabin layer change from tantalum to nickel iron chromium onto the output voltage profile for the Planar Hall effect, it shows a difference in the output voltage, and this difference is regarded to the change in the active current value, where the applied current is distributed onto 2 currents: the active current passing through the nickel iron as a ferromagnetic layer, and the shunt current passing through the other layers, where the resistivity for the nickel iron is higher than the resistivity of the tantalum. A difference in the shunt current magnitude differs, and subsequently the active current, and where the output voltage is correlated and associated with the active current value, a difference in the output voltage can be obtained, and it was regarded to the reason as mentioned earlier. To sum up and to conclude, we conclude that the tantalum replacement to nickel iron chromium results in an enhancement or increase in the exchange bias value 1.3 times as a seed layer and 3 times as a cabin layer. The substitution is results in the improvement of the ferromagnetic layer's crystallinity and the reduction of the dislocation density into the ferromagnetic and antiferromagnetic layer interface. The reduction of the coupled area between the nickel iron and iridium manganese layers was affirmed as well by using the cabin layer, and the shunt current reduction leads to higher values of the output voltage due to the increase in the active current value. And finally, the highest signal to noise ratio achieved was with getting the tantalum as a seed layer and nickel iron chromium as a cabin layer combined together with the trilayer structure mentioned earlier. This work was performed in Emerging Material Science Department in Daejeon, Korea, with my supervisor and group members during the PhD time, Professor Sholgi Kim and Dr. Artem Tantsev and Mr. Sunjun Kim and our NiFeCr group. Thank you so much for your listening.